We're going to talk about Green's theorem. Green's theorem can be viewed as a generalization of or extension or an analog of the fundamental theorem of calculus for one variable. So we would like to recall what this theory is in a form that can be it can be shown to be in parallel with Green's theorem. So here's what we're going to do. Normally, the fundamental theorem of calculus is given as a statement that if the antiderivative of f lowercase is f uppercase, then the integral from a to b of f of x dx is f of b minus f of a. And when we give this theorem this way, we obviously focus on the fact that the fundamental theorem of calculus is used in order to help us compute definite integrals. However, the perspective that we're going to adopt here is a little different. And for that reason, I would like to give the fundamental theorem of calculus in a less traditional way. So I would like to just say that if I have a function f that has a continuous derivative, obviously that's true for all functions that we study in such elementary courses, then f of b minus f of a is equal to the integral from a to b of the derivative of f of x dx. This is absolutely equivalent to the statement that I just gave, the more traditional one, but it will serve our purposes better in this form. And one of the things that I would like to do is, first of all, this is a one-dimensional integral. So this is a one-dimensional integral. Over the interval AB. And I would like to view this as a zero-dimensional integral over the boundary of AB. And the boundary of AB is simply the 2 points A comma B. So obviously it is a strange thing to call a difference between the values of a function at the two endpoints to call it an integral. But we could actually adopt a pretty similar notation as for usual integrals. And pretty much we would say that we have the properties that we have for common integral, meaning it's linear and if the function is increasing, it's positive. But in any case, we don't want to overanalyze this. Let's just mention that we have a zero-dimensional integral, and that will prepare how we would like to introduce Green's theorem. Because in Green's theorem, I will have, if I want to make the analogy perfect here, I will have a one-dimensional integral on the left, which will be over the boundary of a domain. I remind you that with partial d, we denote the domain of D and the boundary of D. And on the right-hand side, I'm going to have a double integral. So far, the analogy seems to be quite good. You have a one-dimensional integral on the left and the two-dimensional integral on the right. So the difference between the dimensions of those integrals is 1. And the integral on the left is taken over the boundary of the integral on the right. And here's how it works. I start actually with a simple closed curve. What is a simple closed curve or a simple closed path? It is one that starts and ends at the same point and has no intersection, self-intersection. So starts and ends at the same point and has no self-intersections. Then there is a beautiful theorem in mathematics, which it's one of those theorems that has a pretty straightforward conclusion, but when you try to prove it is anything but simple. It's called the Jordan curve theorem, that says that if you have such a curve, then it separates the plane into two sets, its interior and the exterior, into two connected components, as we say. And pretty much the interior is what I call D, which makes the curve itself the boundary of D. And we also suppose that it is traversed in the counterclockwise orientation. Now, if you have a very, very complicated curve, I mean, imagine that your curve may be doing lots of zigzags in a very strange way, and what I just drew here does not even start describing how complicated such a curve is going to be. You may actually not be able to see very clearly what is interior and what is exterior, or in some sense, what is clockwise and what is counterclockwise. And there is a very nice description, which is that if you stand upright on the plane and you're sitting on the boundary, you're standing on the boundary, then you're facing the counterclockwise orientation if the domain is on your left hand. So that's a very nice description for what it means to move in the counterclockwise way. So we have now to give what the integrands are going to be for the two integrals. So on the left, we have a vector field. So it will be a vector line integral. So this is p dx plus q dy. And this is going to be now equal to an expression that is made up of the derivatives, actually the partial derivatives of the components of this vector field. So it's going to be q sub x minus p sub y dA. And this is Green's theorem. Green's theorem or Green's formula. You can call it anything you like. And I'm not going to treat it as a computational formula. And this is what this is why I gave the fundamental theorem of calculus in this way that I gave it, so that it's in complete analogy with this formula. I would like to treat it as an interpretation theorem or a translation theorem. So one integral is expressed in terms of another integral, or it's made equal to another integral. And it's actually up to us to choose which integral, which way we're going to use this equation. So again, this is a one-dimensional integral vector line integral over the boundary of D, traversed in the counterclockwise way, And this is a two-dimensional, just a double integral. So just a double integral. Over D itself. Okay. So, so as I said, 95% of the times in this course, it's going to be used like this. So again, don't think of this theorem as helping you to compute integrals. It doesn't. What it does is it takes an integral and it makes it equal to another integral. And once you're left with the other integral, it's up to you to try to compute the other integral. So the job of Green's theorem is to actually enable you to do the transition. How you're going to compute a new integral, it's your own business. So let's start with a first example. So compute the vector line integral along the boundary of a domain D that is going to be specified of x squared y plus e to the x squared dx plus xy squared plus x plus cosine of y squared dy, where D is simply the square 0, 1 cross 0, 1, and the boundary of D is traversed in the counterclockwise way. Okay, so this is what we would like to do as a first example. And look, if we are to use the complete strategy that we have outlined for integrals before today, we would have looked at an integral of this type, and we would have said, well, is this a is the underlying vector field a conservative vector field? You can easily see that this is not a conservative vector field. Then you can ask if you can your only resource will be to actually compute it using a parameterization of the path. And here, your path is what? Let's draw it. The path is simply b squared. But exactly because naturally it breaks into 4 segments, you will have to do 4 separate integrals. And when you compute those separate integrals, you will see that at some point you will have to take antiderivatives of things such as e to the x squared. Actually, you will see how this will work out. I mean, if you actually try to do it, because it's obviously impossible to get those antiderivatives. But eventually, the computation can be carried out. It has to be said that the computation can be carried out after doing all sorts of acrobatics, I should say. But it's going to be a long computation. And you have to compare it with what we're going to do right now. So in order to proceed with Green's formula, we have to identify our P and our Q. And we have to be careful with all of that. So P and Q are going to be, P is going to be whatever is sitting in front of dx, Q is going to be whatever is sitting in front of dy, and you have to acknowledge the possibility that the terms do not come in their natural order. So first P, then Q. You could have the dy component in front of the dx component. Actually, the next example that we're going to do is going to be exactly like this. So now you need to compute the quantity q sub x minus p sub y. That's exactly what Green's formula says. This is exactly what you should integrate. And you have a little miracle. Those unknowing terms, e to the x squared and cosine of y squared, completely disappear. So what do you get? You get the partial derivative with respect to x of x y squared plus x plus cosine of y squared minus the partial derivative with respect to y of x squared y plus e to the x squared. And what is this equal to? This is going to be equal to y squared plus 1 minus x squared. So what do we need to take? We need to take the integral over d, this is d, of y squared plus 1 minus x squared dA, which becomes a iterated integral. And this is such a simple computation. I mean, you can actually tell right away that the integral of y squared, if you isolate y squared, is going to be equal to the integral of x squared. The letters do not matter. They're pretty much the same function with variables reversed in a symmetric domain, which is the same that it is in x as it is in y. Those two will cancel out and you will only have the integral of the function 1, which will give you 1. But, let's do the computation. We can show how this is done in an iterated way. So you will have x y squared plus x minus x cubed over 3. And this has to be computed from 0 to 1. And then go dy. And this is the integral from 0 to 1 of y squared plus 1 minus 1/3 dy, which is y cubed over 3 plus y minus y over 3 from 0 to 1. And this will be pretty much 1/3 plus 1 minus 1/3. These two things cancel each other, and you're left with the number 1. Okay, and that's a very, very simple application of Green's theorem. Let's do one more example. So compute the vector line integral of x cubed dy minus y cubed dx on the boundary of a domain D, where D is the unit disk and the boundary of D is traversed in the counterclockwise way. And see what the solution is, right? So again, let's draw the domain and its boundary, which is traversed in the counterclockwise way. So the interior is the domain D and the circle is the boundary. Let's identify P and Q. This is P, right? With the negative side, minus y cubed, and this is Q. So we will have that Q sub x minus P sub y is the partial with respect to x of x cubed minus the partial with respect to y of minus y cubed, which is going to be 3x squared minus 3y squared, which is 3x squared plus 3y squared. And that's all we need to integrate over the unit disk. So we will have the integral over d of 3x squared plus 3y squared. And in some sense, we should even completely disregard what came before this. That is, we should look at this integral and realize that this is now our starting point. So somebody gives us this double integral over the disk. What do we do? And we have an obvious choice here to go with polar coordinates. So the domain is dealt with very easily. So it's the unit disk from 0 to 1 dr, from 0 to 2 pi d theta. The integrand is 3x squared plus 3y squared. This is the same thing as 3x squared plus y squared. And we know that x squared plus y squared in polar coordinates is r squared. So the integrand is 3r squared. And of course, we shouldn't forget the Jacobian, which is r. This integral certainly splits. It's the integral from 0 to 1 3r cubed dr times the integral from 0 to 2 pi d theta. And this is going to be 3/4 because the antiderivative of r cubed is 1/4 r to the 4th times 2 pi. So the whole thing will be 3 pi over 2. And that completes our computation and our second example and our video. Thanks for watching.